Go. Everybody's enjoying the nice, beautiful day outside. It is absolutely gorgeous. It's almost a tragedy to be in here doing some learning, but at the same time, it's nice to be in a place here in Colorado where we got nice, beautiful weather. I hope everybody's doing well. If you guys have friends or family out in Kentucky or any of these areas that have recently been affected by storms, heart goes out to everybody out there. I got some calls and some texts from friends that recently got hit from those storms, so hoping everybody's doing okay otherwise. And there we go. Chat should be working for you. Get my screen up here, and we're about ready to get started. Cool. Oh man. Well, I can't say that it is tough to be a Colorado sports fan these days with the Avs out and the Nuggets out. All we have left is the Rockies right now, and that's tough to watch. That's a little rough at the moment. If anybody's made it to a game, but I hear Coors Field is the best bar in Denver, but I don't know about the rest of it at the moment. All right, we'll give people a couple more minutes here to settle on in. All right. Okay. Fire department's coming through. Give that a second here. Mhm. All right, we're about a minute past, and let's be respectful of everybody's time and jump on into things here. So, first of all, thank you so much for joining me on your lunch break. My name is Andre Hayen. Today, we're going to be talking about interior horticulture and the energy code. Specifically, we have this titled as "Growing Your Own Program." Now, tongue in cheek, viewers will know exactly what we're referring to, especially in Colorado. That is probably more than just indoor agriculture. That is also some of those cannabis grow house facilities and things like that, to which there is a growing need for the code to be able to address and identify energy concerns associated with those buildings. And so the phrasing that we put on this of grow your own program is really meant to explore today. We're taking a high level approach to go over some of the key things that the energy code between the 21 and the 24 version are impacting or expanding some of their impacts on when it comes specifically to these particular types of buildings. And so we're going to try and meet everybody where they're at. There are some folks here that are probably going to be kind of old hat at this. They've seen quite a few of these. Maybe they've specialized in energy approaches to some of these buildings. I know we'll have folks that probably have not seen too many of these or were on an older code where energy wasn't as big of a focus on that. And now that they might be looking at adopting, say, that 21 or 24, now that this whole process with the state is coming to a close and the CECB, they might be looking at how they're going to inform the approach on these sorts of things and how that's going to affect this. So today we are going to be looking, like I say, high level approach. We're going to be talking about some of the big picture sort of items. And then if it's something that you guys find helpful and useful, then please throw it in the comments, throw it in the chat, throw it in your survey, and let us know if this is something you'd like to see us follow up on with more components and pieces. So we'll kind of go over the agenda for today here. It's kind of the next stop on this. So we're going to talk about, what this is. What is interior horticulture? What are we deciding? What are we discussing when we talk about that? And how is that going to impact the codes? How does it impact energy code? Why are we talking about this at all? The energy code for a basis and basically all codes for a basis are typically interested in people, right? People for life safety, people for sanitation, health, welfare, all of those components. So why are we talking about plants and why would it matter in this case, right? Then we're going to talk about some Plants 101. Like I said, we're going to get down to brass tacks on some basic science associated with this, how that's informing sort of different approaches in the code that wouldn't have been used previously or wouldn't have been the focus of the code previously, and how the needs of plants are sort of impacting the way that we look at our systems. I'm going to hit some key highlights on three main parts of the code that I want people to be aware of and thinking about as they try and integrate more of this into either their inspection procedure or their plan review and just have their ducks in a row in terms of what policies are you going to implement, what strategies are you going to use to gain healthy compliance in something that I would kind of describe as sort of a square peg, round hole sort of scenario. Not everything associated with these buildings is expressly enumerated in the code. We've got some really interesting specialty systems and things like that that you have to be aware of. And so, like I say, we're going to touch some real high level science and some real high level basics associated with this and kind of break down those three items. So that's what I've got for you for today. And so, like I say, if this is helpful and you guys would like to see that in much more depth, please let us know. This is the first time we're taking a stab at this, and I really hope that it's helpful to you. So we'll go ahead and jump on in. What exactly is interior horticulture? Well, the 21 and the 24 codes are the first codes that really start to broach this from an energy code perspective, where we're talking about the cultivation of plants. Now, that can be for, plant consumption, that can be tomatoes, that can be garlic, that can be, grapes, it can be all kinds of things. It can also be recreational drugs that are legal in certain parts of the country, like here in Colorado, where we have cannabis growing facilities. This typically requires a few key components. We're talking about very precisely controlled environments in order to be able to support the kind of ecosystem necessary for these plants to grow. Because remember, this is a cash crop. Whatever they're growing, whether it be tomatoes or cannabis, whatever they're growing is effectively a cash crop, and people need to make money on this. So they are very much into the science of how to get the best yield possible. And so that comes with very precise requirements that they have in terms of their business needs and a lot of energy intensive equipment. So that can include things like humidification, dehumidification, additional ventilation, a number of different components there. Very specialized lighting requirements, and we're going to get into a little bit of that and break some of that down. And also irrigation systems. Now, that one's mentioned here. I don't really go down further on that because it's outside of the scope of the energy code. But if you're looking at also perhaps adopting some green code measures or things like that as you look at the 24 and how that might inform some of your policies, just to make you aware that that's also obviously a major component of this is how are we using that water? Are we using any gray water or water collection systems as part of this as well? So just to keep you kind of abreast at that high level on the topic of what all are we considering, what all are the parts or the major components of this discussion. So like I say, this can be indoor farms, this can be outdoor farms as well, this can be greenhouses, this can be cannabis grow operations, and we have very precise environmental controls and very high output lighting. So this is really where we're breaking down the practice of how we're going to apply the code for this. So we're going to start by talking about how plants work, right? It's really imperative that we have this sort of separate context for us. And for some of you that either garden yourselves or have worked through this process before, this will be old hat for you. For some of you, you may not have touched this for a while since, like high school biology and things like that. And that's okay. We're going to meet everybody where they're at and just talk about why this is going to matter down the road as we get informed about things like light and some of the other sort of business processes associated with harvesting plants, working with plants, things like that. So we have four basic steps here. We have germination, that's when we get seedlings that are actually starting to become plants. We get vegetative growth, that's when you're starting to get stalks, you're starting to get actual plant growth in the form of typically things that are going to be above your substrate when we're talking about things like cannabis, for instance. And we're getting those stalks, we're getting branches, we're getting things that are reaching up towards light to get more and more of it. Then we get flowering or fruiting, right? This is where the plants can be sexed if they want to be mixed with other plants or pollinate. If anyone has ever planted peppers in their garden next to anything else, any other kind of pepper, you know how that can go. You can get really terrible bell peppers. You can get really bland jalapenos because of that, right? Because the flowering process is part of the way that they're going to pollinate, right? And that's going to mix with other plants if that's part of the plant's process. And then harvest, right? That's where we're going to be taking some of these either fruits, vegetables. This could be the buds associated with cannabis, and we're going to be removing those from the plants, and then they'll be set for storage. They might be dried, they might be put into ripening rooms, things like that. And that's going to inform maybe some of the rooms or separate business processes that we have on one of these facilities. And so we have to be aware that these are all, as much as they are life cycle stages for the plant, they're also business stages for kind of what's happening in terms of our systems and how this is going to be impacted. So from a basic level, right, plants need a few things. They need light, they need water, they need carbon dioxide, and they need nutrients. Nutrients are typically in the form of a substrate that they're going to grow in, like a potting soil or some kind of soil, right? That can be clay, that can be a number of different things based on the needs of the plant that we're talking about, right? That can also include chemical fertilizers, that can include a number of other items that help that plant get what it needs in order to be successful. This whole process is brought to you by photosynthesis, right? This is where plants take light and they turn it into chemical energy. That energy is then stored, put into flowers, put into other parts of the plant, and turned into the fruits that we eat, the vegetables that we eat, things like that. And in order to do this, temperature and humidity need to be controlled exceptionally well. So that's where we get into that precision issue. We also have lighting to contend with as well. So lighting, when we talk about plants, what they really want is scientifically, man, that is not an easy word to say. Photosynthetically active radiation, or PAR, which I'll be referring to it for the rest of the presentation to make my life a little easier, is the light spectrum that plants actually use, right? And we're going to talk about that, how that informs the type of lighting that's used in these areas, why it's treated differently in the energy code, and why we use different means to be able to determine whether or not it's actually high efficacy. So a number of artificial lights now cross the light spectrum in these areas, these nanometers, right, for this light spectrum, for these plants to be able to grow. So that can be LEDs, HPS, which is high pressure sodium, or fluorescence, can be used to replicate sunlight, each to varying degrees of success and varying degrees of efficacy. Light intensity and spectrum are what really are going to affect plant yield and growth from a lighting perspective. So this is a place where there's a lot of scientific research. There's a lot of desire from the communities that work in this space to have really high tech components, and the kind of things that they need in order to ensure that they're going to be profitable at the end of the day. And so that's really informed sort of the discussion in the code as things have continued. We also need stable climate control, like we've talked about. So that is airflow, that is humidity, that is temperature, and HVAC systems are going to be used to monitor and change a lot of this, including dehumidification. They mention here dehumidification is critical in the late vegetative and flowering stages. Too much humidity at this point is where you can get mold on plants, you can cause whole crops to fail, things like that. So we have need for both a high humidity environment and also the ability to dehumidify in order to control that process as it corresponds to the life cycle of the plant. And all of these items can be major energy consumers. There's no getting around it. So, first things first, we'll talk a little bit about the building code with this. And obviously, this program and the presentation that I have to you today is really focused on the energy code. And I will say, shameless plug, I do have a boss, Steve Thomas, that effectively wrote the book on this topic. He gives a great presentation on how grow facilities are impacted by the building code and the kind of things that need to align between the building code. But from just a high level perspective of how these components are going to affect the energy code, this is what I've laid out for you. Is number one, your building layouts are going to have a number of different changes to them than just being a typical greenhouse at times, especially when we talk about cannabis facilities. This can be limited control access areas. This can be additional storage facilities or storage areas that have limited access control as well. This can mean a number of chemical fertilizers, stripping agents when we're talking about extraction facilities. So some of the components that I want to bring up here and just make you think about or make you aware of is this is a place where it really matters, where the building code isn't just going to say, I mean, you could do the entire process according to the building code, right? From growing marijuana to chemically stripping it to its distillates, if you'd like to sell those, right? If that's the business process that somebody is going through, to storing those things to having retail space, right? You could divvy up a building with the right control areas, the right fire separations, and you could do that. Typically, what's going to prevent that from happening are zoning regulations, right? Your zoning is probably going to say, hey, you can only have, the grow operation, you can have offices, you can have things like that, but that can't also be your retail space as well. Or if there are separations, that's where that's going to occur. So this is one of those places where fire code, zoning code, and building code really have to get aligned the old-fashioned way, through those conversations with your fire marshal, with your code official, with your zoning director, whatever that equivalency is, to make sure that you have everything you need for these components to be successful from the output. And also then how that's going to inform some of the control areas for things like our lighting, for our climate controls, things like that. So what else is considered here, right? Well, we have things like growing mediums, right? Those can be flammable. Potting soil is flammable. I remember Sarah Carter telling us that at a Division of Fire Prevention and Control training for CCICC, and her face when she went around the room and how many people didn't realize that potting soil was potentially flammable. I will never forget. Definitely sticks with me there. But it is one of those things that for sure we want to keep an eye on, be aware of, that we have high quantities of materials that might have nitrogen, might have fertilizers, things like that in some of these areas, which will then require potentially control areas that might be separate from the grow facility. They might have separate lighting then, they might have separate access, all of that good stuff. There's also requirements for surveillance or security systems. Remember that a lot of components now in the energy code, when we talk about things like exterior lighting, and I'm not going to spend too much time on this today, but safety and security related lighting and things like that definitely can have certain exemptions away from your total lighting power allowances or some of your controls. And so this is a place where, again, aligning policy and making sure that it's very clear on what you consider to be security lighting for a circumstance like this makes sense and is kind of right fit for your needs as a community. We already talked about zoning prohibitions. Another one is backflow requirements with some of those irrigation systems, right? There's a number of places here, and like I said, this is not that building code class. As much as I would like to give that to you because it is a great class, it's also 4 hours long and all of that, and I know we signed up for an hour over lunch today. So we'll keep it short and sweet with that, but it's just some of the places where these things are going to impact your ability to then facilitate the rest of your inspection process and just kind of be aware of what's happening. The other thing that I kind of wanted to bring up with this is that no matter what code we're enforcing, whether it be the energy code, the building code, the fire code, there is a certain risk about this, right? And that is that we should be recognizing, regardless of our own moral beliefs or implications, that if cannabis grow operations are legal in your jurisdiction, cannabis in and of itself, when we talk about the building code, and I'm quoting Steve Thomas with this, it's no more inherently dangerous than growing tomatoes. It is basically a very similar process with very similar equipment and those sorts of things. So it's not inherently more risky. And what we need to make sure of is that whatever you're doing for right sizing, the right application of code and of requirements, that's being done even-handedly, right? That no one on staff or no one is sort of prejudicially enforcing certain requirements when it comes to things that they might not agree with, like growing cannabis or, in Denver's and Denver area, I should say, now there's the option for psilocybin mushrooms as well. Those have been decriminalized, and there's some places growing those. And so again, this is just one of those places that whether you agree with it or not, we want to be even-handed because nothing's worse for a building department than running into a circumstance where you're getting into that prejudicial enforcement sort of concern or lawsuit or things like that. So just to remind everybody, this is kind of the big push to make sure that you're looking at the code very even-handedly when it comes to this. So what about the energy code? Well, from the data that I can find out there, indoor grow facilities can use 5 to 10 times more energy per square foot than typical buildings. Now, typical buildings is a vague phrase if you're looking at that part of the presentation going, what does he mean by that? And I'll tell you. The data out there is a little tough to find. So, for instance, I found a case study of a 5,000 square foot building in Boulder County with a energy consumption around 42,000 kilowatt hours per month. Whereas a commercial space of about similar use, which again, uses don't always line up with what we look at in the building code and what we look at in terms of energy consumption, but significantly less than that, around 5 to 7,000 kilowatt hours. So that's around 7 times right there what the difference is between those two. So when it comes to size, we are talking about, potentially a pretty energy intensive use. And that comes from the, mechanical systems that we've already spoken about, horticultural lighting systems. And so really when we talk about this, I want to push this concept or this narrative that what we're looking at in terms of, oh, sorry about that. What we're looking at in terms of energy code is to really highlight the intent of the code. The intent of the code is to apply and right size certain efficacy requirements, like this horticultural lighting definition, and then try to make sure that what we're doing is producing cost-effective efficiencies. And we'll get more into sort of the energy use as this like group of buildings as well. I've got some numbers for that down the road that we can highlight as well. But there's just no getting around it that these are energy intensive uses by and large. So let's start breaking this down. What's in the code? So in definitions here in the IECC, we have a greenhouse that had an additional section of definition put in the 2021 to clarify that greenhouses are what we consider to be those permanent structures, right? Not falling into that 180-day definition that we typically use in Chapter 1 of the IBC to discern what's temporary versus what is permanent here. So greenhouses are thermally isolated, and they get some opportunities out of the energy code to be treated a little bit differently, kind of like low energy buildings. So they're in that same section in 402.1.1, subsection 2 here is where they live, right? And so if we heat them, we do get some exemptions from thermal envelope requirements. However, we also get some specifics of what they have to comply with. So exterior opaque envelope assemblies, we have 402.2 through 402.5, unless it's a low energy building, and that's defined by the amount of BTUs per square foot used in that area, right? We also have these two items right here where interior partition thermal building envelope assemblies that separate a conditioned space from the rest of the grow operation or the grow space, the greenhouse space, are going to be subject to 402.3, 402.4, 402.5. And then our fenestration components as well are going to meet these basic requirements here, and that's skylights and ventilation, and we have them listed for you. So remember, we're talking about thermally isolated, typically separate buildings. They don't have to be as long as they're adjacent or abut a place where we do have full compliance with the typical requirements out of the energy code for those interior partitions from those other conditioned spaces. But it's about recognizing that, yes, greenhouses do already kind of get treated differently. And remember that we also have some new definitions that come in the 24. So we take that and we sort of, I won't say complicate it further, but we sort of parse out those differences where we talk about, okay, greenhouses aren't all grow operations. So they add a definition for indoor grow. So they say space other than a greenhouse that is exclusively used for and essential for horticultural production, cultivation, and maintenance. So like I say, new in the 24, and that's one of the places that we start to parse out this idea of indoor grow from greenhouse. In the 21, it sort of is that greenhouse definition, and then there wasn't really good supporting language to discuss those instances of using an indoor space for like hydroponic growth or things like that. We also got a definition for horticultural lighting, lighting used for horticultural production, cultivation, or maintenance. So we get two new definitions in the 24 that are going to help us parse out exactly the applicability of this. And so indoor grow and greenhouse would still fall under that horticultural lighting definition. And we'll see that brought up even further when we get to things like our total power allowance in that discussion, where we see that task lighting for plant growth is one of those things that's enumerated as an exception. So we'll get to that a little bit further down the road. So right now, I just want to take a quick pause. We're 20 minutes in. I know I'm hitting you guys with a lot of information. Any questions to start off about this? Otherwise, we're going to move now into wall assemblies. So if you have anything, feel free to toss it in the chat. I know usually we try to do a little bit more of like a discussion-based sort of class, but this one I just want to make sure that I'm getting that information out to you and answering your questions as you have them. So, please feel free to jump on in. Otherwise, I will keep on cruising to that next section. Okay. So let's talk about wall assemblies. Now, one of the things that it's really common to see in grow facilities is PEN, that's polyethylene naphthalate, or Mylar, as we'd often refer to it. Oh, Aaron, you had a question. Would a greenhouse added onto a residence that's not intended for commercial use fall under these codes? No, so this would be specifically for commercial greenhouses. I'm covering just the commercial sections out of this, Aaron, out of the 21 and the 24. Otherwise, that would not really affect it. I'm sure there's some overlap on sort of there's typical things that are available in the industry when we get to things like lighting and things like that, but all of this is directly coming from the commercial sections, and greenhouses wouldn't really be identified for like out of the IRC, for instance, if you're building out of that and putting a greenhouse on your property. So if it's not used for commercial use, then no, this wouldn't kick in. Great question. Absolutely great question. So yeah, Mylar is one of those items that's typically put into a lot of these grow house facilities on the interior wall assemblies. And the job of the Mylar is multi-purposed. It is trying to seal up the area around the plant. It's trying to reflect that heat back towards the plant. It's trying to make sure that that humidity in that environment is basically kept separate from any other part of the wall assembly or anything else, and they're not leaking sort of the energy that they're putting into trying to keep that plant, moist in the correct sort of humidity for the environment, and simultaneously, like I said, reflecting that heat back. But we also know, as we've talked about, and as many of you who have been with me for class after class after class, we've harped on and talked about some of the specifics about vapor barrier and vapor retarder assemblies and how they're used in wall assemblies for best effect, right? Because we want to make sure that we're creating dry walls in these environments. No pun intended there for gypsum board, but we are trying to make sure, right, that what we build has an ability to breathe. And so the way that we do that with modern tight construction is we're very careful about where we put in any class one, class two, or class three vapor retarders, right? Based on that and our insulation, that can create an unwanted dew point in places, or we can vapor lock a wall that way, where that moisture is basically told on both sides there is no way out. And that's how we get those interior rots and things like that. And unfortunately, this is something that a lot of grow houses are just absolutely famous for, especially the illegal ones, especially the ones that maybe have been built into construction that wasn't really ever designed for this sort of use. And so it's a place that I want to spend a few minutes on today because I think it informs a lot of the discussions about potentially modifications, for existing buildings in Chapter 5, and then also sort of our tack when it comes to some of these items that aren't going to be there when we do our CO, right? You're not going to see Mylar on the walls at that point. You're not going to see this up until later on in the process. And so planning for this in advance could really save that building in terms of rot and damage over its lifespan. So here's a funny story with this, though. Mylar obviously is not a typical building material. And so I had to do some interesting digging to go find out what is the vapor transmission, moisture vapor transmission level for Mylar. And so Mylar also comes in a number of different configurations. And what I see to be really common in these conversations as I researched for this class is that they like to do a Mylar laminate film with a foil. And now we all know foil is a class one vapor retarder that's borderline impermeable, right? It's one of the most impermeable things we have. Really, the only places where it has any permeability is at seams, joints that aren't sealed properly, and penetrations in it. Otherwise, it is pretty much a complete seal. And so what I ended up finding here is something kind of interesting. This is from a declassified CIA report from the 60s and 70s, when they were looking at Mylar testing in association with some aircraft stuff, some NASA stuff. I mean, some crazy stuff out there. So yeah, that is the research that I got to do for you this week that probably put me on a list. And now that you all see it, you can be on that list with me now. But yeah, the water impermeability on this particular material is exceptionally high. They came out to 5.5 grams of water per square foot per year, which is insanely low water transmission. I know some of you guys, I didn't include it in this slide because it's kind of a residential oriented slide. But some of you have seen sort of that Joe Stiebrick article or that slide that Hope put together where you can see the liters of water penetrating a gypsum board assembly. And if you cut the 1 inch hole in it, you can see that it's liters and liters and liters of water compared to what it was before. This is significantly lower than that. Then I was able to find a little bit more as I kept digging here. And again, we're in the same sort of place because I pulled this from PNNL and Homeland Security, who again were looking at water and vapor transmission rates for some of these polyethylenes, polynaphthalate, which is that PEN. That's the actual like chemical designation for Mylar. Mylar is actually a DuPont brand name. So just to make that clear to everybody, if we talk about that, when we talk about Mylar, we are talking about sort of using that brand name like Kleenex versus tissue kind of thing, right? But yeah, the water impermeability of just the naphthalene, or excuse me, the naphthalate, is already exceptionally low. And then when you add a foil facing or a laminate like that, that can get very low. And so you see here, this is a statement from DuPont. Let me turn on my little laser pointer. Mylar polyester film is virtually impenetrable or impermeable to liquid phases of most chemicals and reagents, right? And now I think this is an important one to realize is that like when you talk about a grow facility, we're going to be talking about other chemicals that are associated there. Things like CO2 and CO2 enrichment or ozone or some other things, because they're not worried just about air and water like a typical building is. They're also worried about these other gases that they're filling in this room for enrichment purposes for these plants. So being mostly impermeable to a number of chemicals and reagents is actually really important to them and really important to the kind of materials that they select. So that informs this process. But it also then starts to explain why a lot of grow houses suffer from high mold issues. So remember, taking this back, and I won't spend too much time on this, if you jump back to IBC section 1404, you're going to see your wall classifications, your wall assembly classifications for your vapor retarder classes. And so we've already looked at this, right? And we've seen sheet polyethylene on there, non-perforated aluminum foil. This would very much fall under that vapor retarder class of 1, right? These are exceptionally vapor impermeable items that we're talking about here. Then we have our craft face, our latex paint, right? Our other much more permeable layers of vapor retarders out there. Just as a reminder for you, if you go to 21.1404.3, that's where you're going to see your class 1 and class 2 vapor retarders here. And you see already that it's identified in the 21 that we're going to be kind of careful about how we go ahead and use a class 1 vapor retarder. In this case, identifying that in the exterior side, it shall require an approved design. And so an approved design can be a number of things, right? It can be something that you've seen used in the past, something that's very common to the area, and there are a number of these that can work. That's a viable option. Oftentimes, this might require things like a dew point calculation. And so this is one of those places where, again, when we talk about growing your own program in square peg round hole, there aren't many instances that I can think of where you're putting a class 1 vapor retarder on the inside of the drywall system, but that's exactly what you're doing in this case. And so making sure that we are kind of right sizing that if that's the method that's going to be used for some of these grow operations, that it kind of makes sense for the way that the rest of the wall is built. So there's some breathability in these other portions. If we jump over to the 24, we get a little bit of a rewrite on that section, and I didn't highlight everything that got rewritten. I kind of tried to just focus a little bit on the vapor retarder here, specifically to our climate zones, and we get this new table here of 1404.3.5, which I'm just highlighting for you because this is meant to align with the changes in the energy code as we've added more systems that can allow for exterior mixed insulation systems, right? Because the entire design of that mixed insulation system is that your dew point being created by your rigid insulation or your spray foam insulation, whatever's considered to be continuous and non-permeable, that particular part of the material assembly is informing what materials we're going to use on the inside. And just to highlight the physics for everybody that I know you've seen before, this one on the left is probably not as likely. This is, the way that we like to keep buildings, where we talk about the indoors being kind of cool and dry in the summer months, whereas it's more warm and humid in maybe other climates, sometimes here in Colorado, but definitely not nearly as humid as others. And so we get that condensing surface identified on where that's going to be. Now, here, right, in indoor warm and humid climates, which is probably more likely when we're talking about a greenhouse condition versus a cold and dry outdoor climate. Now, that is sounding a lot like Colorado and a greenhouse or a indoor grow operation. We can see that there's a vapor drive where that vapor wants to penetrate through these assemblies and out to where that energy exchange can occur, right? All heat wants to move to cold, everything wants to normalize in the universe. That's our basic physics, right? And so we know that if there is moisture in this wall assembly, and there's always moisture in wall assemblies, when it gets built, there's going to be moisture in that wall assembly. Any penetrations from any of the rest of this into this wall assembly is going to help carry moisture through. And then, of course, anything that's entered during the typical sort of exchange of moisture into wall assemblies, right? So this is kind of both sides of that vapor diffusion. When we get rain, we get water vapor, we get the built-in moisture, we get the moisture associated from the use of the building. This is where that can really complicate those things, where we have this interior impermeable system. So this is a wall system that I just obviously created in kind of like an MS Paint thing, just to give you guys kind of a reminder about this. But if we're talking about converting existing buildings, this might be a perfect example. Maybe we have brick on the outside, maybe we have sheathing, and then we have our studs, we have drywall, and now we have mylar on the inside. And now if we have vapor impermeable insulation somewhere in here, any moisture in this cavity doesn't really have a place to go. It will just sort of cycle in this cavity. And so we want to make sure that we're trying to tell this where to go and giving it a direction out if we know that's sealed in here or sealed in tight to the drywall. Maybe we're going to use some of the other assemblies that are out there. So I did find in commercial settings for this, a lot of folks have gone to antimicrobial, like vinyl wall panels and things like that. For the really like brand new ground up commercial greenhouses and commercial grow operations, they've kind of headed that direction. So, depending on what materials are used here, that's going to be a level of potential vapor impermeability that's going to be different from your typical construction. And so making sure that there's breathability at some other point in this wall assembly is going to pay dividends. Because we know what happens when it doesn't happen, is the next thing I want to bring up, right? The impacts of mold and poor ventilation in these assemblies can be pretty catastrophic. So right here, we have a business that almost went under over this mold and yeast growing on their plants for 54 different dispensaries that they had to recall. Right. And at the end of the day, no matter what kind of business opens up in your jurisdiction, I'm willing to bet, like you and like any other code official I've ever known, you want to see businesses grow. You don't want to see businesses fail. You want to see your tax base grow. That is part of our charge and part of our duty. And so, seeing this could definitely put somebody under for a small business, right? This could be, making it or not. We also see that there's an arrangement of circular fans out here. And these fans are meant to circulate the air, blow off some of that moisture, right? And hopefully coalesce with some other ventilation systems, right? And now I don't spend too much time on that because you can go down a rabbit hole when it comes to the mechanical systems. And like I said, I want to hit the high level stuff for you today with the hour that we have. But I mean, you can imagine how DOAS systems, ERVs, right, that can help condition and also take out some of that humidity, provide a dehumidification process as well, can really inform how we're going to use these spaces effectively. But if they're not planned very well, then we end up using a lot of systems that are probably energy intensive, a lot of box fans, things like that to circulate that air, which then adds to the overall energy intensity and use of that occupancy when they could have had a better plan for their wall assemblies, for their ventilation processes, and how they're going to work on that. And then here you can obviously see the reality of what can happen when buildings are just not planned for this at all and the impacts of these individual grow areas just growing mold and mildew against every wall. And now, if you're the building owner, now you have abatement issues. Now you have concerns of, how much mold mildew is there. This is the kind of thing. Now, obviously, this is more use oriented, end use oriented than maybe we would have seen as building officials when this building was built. But if we're getting those permits for folks trying to come in, trying to start their business the correct way, we can have this conversation early on to inform them, hey, if you want to avoid mold, it's good for your business. It's also good for us that we don't see abatement after, you might change to a bigger tenant space down the road or something like that, based on the construction that's there and based on having these conversations with the wall assemblies. So here we can see the absolute worst of it, right? And so on the right, we have a residential home. On the left, we actually have a commercial building with the polyethylene stripped down. And so we can see where moisture was trapped in these wall assemblies between the polyethylene and then resealed again over the drywall when they decided to hang the Mylar system up. And then obviously a lack of a permeability on the exterior there. So this just was not exchanging. This became our dew point, and mildew abounded in this area. So we can see over and over again the problems associated there. This was a picture I actually borrowed from Steve himself, and this informs sort of that worst case scenario for an illegal grow operation in a residential home, where none of this was planned for, clearly inadequate ventilation, and you can see now that this homeowner has significant amount of work to do to try and address these concerns and these issues. So with that, I'm done on wall assemblies for now. I think that that's hopefully a good place to remind folks that this is an important conversation to have. And now I'm about to move on to lighting. So, with that, we've got our basics that we normally look at for lighting controls, daylight zones, lighting power allowances, right? These are the typical things that you're going to point to for most of your operable lighting within buildings. Now, as you jump over to this, the first thing that you normally do is figure out, okay, how much connected total interior lighting power do I have? So I can start to do my calculations on my lighting power allowances and all of that good stuff, right? This would be the first space, but if we jump over to this, one of the things that we're going to see is we're identifying task lighting for plant growth or maintenance as an exception. Now, I'll be frank with you, this has been there for some time. It's been there for, I think, 3 code cycles written this way. I do wish they would have just referred to it as horticultural lighting now that they added a definition for it in the 24, but beggars can't be choosers. We have the information that we have. And I think we have that discernibly identified as code officials to say, okay, we're going to have to figure out what type of lighting we're using for this. And then, so what informs this now? If this is exempted from my lighting power calculations, if this isn't used for my interior lighting, how do I regulate its efficacy? How do I understand how much efficacy it needs to have? So we have two definitions here. If we go to the 21, we get one here that says not less than 95% of the permanently installed luminaries for plant growth and maintenance shall have a photon efficacy of not less than 1.6 micromoles per joule, is what that means for you. For all those non-science majors like me, I definitely had to Google that one. So 1.6 micromoles per joule. Now, that's interesting. Let's compare it to the 24. And here we have 405.4 horticultural lighting. So now we're using that defined term again that we got in the 24. And so we actually have kind of a separation here. So we have greenhouses identified as having now 1.7 micromoles per joule. So that number's gone up. Is that good or bad? Right? That's one of the things that we have to look into. The higher this number is it better? Is it more efficacious or is it less? Right? And not less than 1.9 micromoles per joule for all other horticultural lighting. So that identifies then our indoor grow operations based on those previous definitions that we got, right? So that helps us identify, okay, greenhouses we treat a little bit differently than indoor horticultural lighting. We also have some control related items. So luminaries here have to be shut off when there's sufficient daylight available. Now that's an interesting way to phrase that to me. And I would posit to you guys if you see this differently than I do. But the way that that's written, that tells me that that could be a daylight sensor, right? That could be something that picks that up and says, okay, in the greenhouse, I've got, translucent opaque assembly, partially opaque or semi-opaque assemblies, right? It would be super normal for a greenhouse to let in a lot of daylight like that and take advantage of that. So in the times when that's available, that could be a daylight sensor. I also read that in the sense that that could also be a timer because it doesn't expressly say it shall be daylight sensitive. It just says that when there's sufficient daylight available, if I go off of a clock and I set it in a certain way, sure, I could guarantee that to some degree. But it is one of those things that probably will come up for interpretation or discussion at some point. And as of right now, I've looked in the commentary, this is relatively new. And as far as enforceability goes, that's a good question in my opinion, exactly how you would interpret that, whether that needs to always be a daylight sensor or not. Because the next sentence does make the compelling case in the opposite, where we expressly say that we will have a luminary turned off at specifically programmed times. Now, to me, that does make sense if you think about it in that context, because if we're doing an indoor grow and we're doing all artificial light for it, then daylight is not an option. So now we're turning these off and on based on a clock. There is no way to regulate daylight for that same way. So that's my 2 cents on that area, but we still have some questions here. Like, I don't know about you guys, but my first question was, what is a micromole per joule? What does that mean? And so what it is in horticulture is the number of photons in micromoles that are produced per joule of energy consumed. So this is sort of like a gallons per mile sort of relationship there, right? It's how much energy is it taking and how much am I getting out of it, right? And the photons are evidently the way that we measure that for plants. So I did a little more digging on this. And so what we find here is that lumens, I think you've heard Hope say a time or two, lumens are for humans. Lumens are a direct measurement of how much visual light intensity there is, basically how bright something is. It's not at all, that's why you get it on flashlights, right? You get 1,000 lumens or, 600 candle feet, things like that. That's really telling us how intense that light is, how far that light can throw, right? But it's not necessarily telling us how much energy it's using. So a very high lumen output flashlight might burn through D-cell batteries really quickly. Meanwhile, watts are a measure of the amount of energy it takes for that light source, right? How much it consumes. And so watts, when we talk about PAR, what they really want is for watts to be as low as possible. That's going to be the highest efficacy, while at the same time creating the most amount of PAR. So that's going to give them the most amount of bang for their buck, so to speak. And that's why we use this, is because photons are what plants crave, right? It's not lumens, it's not watts, it's photons. And so that's the measurement that we're going to use to describe what lighting is efficacious in the circumstance. So how did this come to be, right? And I'm going to give you guys the quick and dirty background on this because I think it is actually pretty interesting. So this actually dates back to about 1991 and a Japanese scientist. And I had his name here written down in my notes, but I think I lost it here. If I come up with it, I will definitely throw it back in the chat or something. But he came up with the blue LED in 1991, which was a big deal. There's actually an entire documentary just about making the blue LED. I cannot stress enough how important this was because once there was a blue LED, we could make all kinds of light with LEDs. We can make white light, we can make yellow, we can make green, we can make every color of the rainbow. That's when, TV technology also took off for using LEDs and things like that, is they immediately took that technology, started putting it into R&D for how we have cheap televisions to this day that are LED screens and your computer screens and all the rest. LEDs were a game changer in this. And so 1997, they actually take these up to NASA. And so they're borrowing some of that information where they're trying to grow plants in space in obviously completely artificial lit environments. And what they're finding is that by using a mix of blue and red LEDs, they could make the lighting significantly more efficacious for growing plants. So that all happens in the, yes, Isma, thank you so much, Guadalupe. Yes, thank you so much. For those that haven't looked in the chat yet, Guadalupe put the name of the scientist in. So thank you. That's huge. I do appreciate that. It's super interesting because previous to that, there weren't really, basically, they were all taking lights from any other component, any other piece that they had, right? So that's why if you've ever watched a movie, that has sort of like the stoner guy that's growing marijuana in his college dorm room or something. They always have like the heat lamp, like the sodium heat lamp or something, over their plants. If you watch a movie like that from the 80s or 90s, that's exactly why. It's because that's all that was available in terms of market. So it wasn't until about the 2010s that all of a sudden we're starting to really replace some of these other types of lighting and use these different sources of light. And so why does it matter? Why we have the spectrum of light now? Well, this is the visible spectrum of light to the human eye. It's this big, tall, bell curvy looking one down here, right? So that's everything that we can see, down to violet, all the way through the rainbow, right? Plants actually have germination. Remember that slide that we had earlier with the arrow and the um, different steps along the way? Well, the different phases of the plant correspond to the amount and type of light that they do best with. So blue light during the germination phase is actually super important, and as you get towards the end of the flowering and the harvesting process, it's red light that's actually more necessary, and the plant needs to have more available in order to be successful. So being able to do that with LEDs really became a game changer, and now we're going to take advantage of it in our energy code in terms of demonstrating efficacy. So it's an imperative there. It also informs you that some of the most efficacious sort of systems out there are shooting for about 2.5 micromoles per joule. So that means that yes, as you go up in micromoles per joule, it's a more effective or more efficient system. So to make you guys aware, these are some of the common ones out here. I borrowed this from the ICC code and commentary here, so you can look this up yourself if you have questions or you want to follow up with this. But metal halide lights are about 1.6 micromoles per joule. So this is really going to eliminate the use of those when we look at the 24. And high pressure sodium, that's probably going away too, except for this double-ended 1,000 watt. So otherwise, LEDs are probably going to be the thing that fills this sort of cavity, so to speak. It's 150 to 650 watts, and we're getting the most amount of output in terms of micromoles per joule. So it's really the most efficacious system out there. And this is what a lot of the industry is leaning towards. And so this is a lot of what you will see when you go to enforce this section of the code. So for a quick and dirty summary for you here, and we'll keep it pretty light because we are definitely going over on time here. I'll try and pick it up a little bit. In the 21, if that's what you're adopting or that's what you're on, it's the 1.6 micromoles or better for photon efficacy, which puts everything in that table on the table for you for use. If you're looking at the 24, greenhouses have to be that 1.7 or better. That allows things like that high pressure sodium, and you have to have something to turn it off when there's sufficient daylight. Other horticultural uses, 100% need to be 1.9 micromole or better. That's basically taking you just to LEDs, and you're required to have time controls. So that's your quick and dirty summary of what you have there. When we talk about lighting within a building, for instance, right? Remember that grow areas are not just like warehouses anymore. They're not just one use. Especially with some of the other things that you have. If you have multiple chemical storages, then you might have magazines and control areas and all that good stuff. You might have CO2 storage for its enrichment systems. You probably have some form of mechanical room as well, right? You might also have offices associated with this space. Because for those areas, we're definitely going to go back to our interior power allowances and we're going to use them just as they are out of the code for those specific areas. I'm not going to go over everything associated with like daylighting, daylight controls, and all of that because I really didn't think it would be too germane to this kind of thing. I think that a lot of what you would see is a lot more of like the employee lounges, private offices, break rooms, restrooms, storage rooms, right? A lot of the other spaces that you'd find to be typical with a grow operation are going to be really occupancy sensor oriented. But of course, you could have some other stuff. Nothing says you couldn't have a conference room nearby and things like that, or a wide open office space. So it's not impossible. I just didn't think it was too germane to the conversation, and I didn't want to spend too much time on lighting here. So I thought something like this configuration where you'd have private offices over here, you'd have restrooms, you'd have some smaller storage rooms with those smaller, less than 300 square foot requirements for occupancy sensors. Just to remind you to keep it quick and dirty there. And then otherwise here, this is one that kind of stands out to me. If you look at building area method, what do you call this thing? I've heard from Steve multiple times his recommendation for a lot of these occupancies is usually that F1 or F2, depending on what you have for chemicals, what you have for fertilizers, all that good stuff. Because really it is sort of a manufacturing sort of output sort of thing, just like most other agricultural, the way that we think about it. And you can tell there isn't really much. You could go to manufacturing facility out of your list for building area and then LPD for your remaining, your remaining lighting as it would correspond. But remember, this is exempted because it's specific to plants. So we have a different method of calculating efficacy. For our other areas where people are in and we're using those spaces, then we're either using the space by space method or the building area method. And like I said before, it's not impossible that you could have an area for grow operations and retail unless, say, your planning and zoning department says that they don't want those things mixing. Totally fair. But if you do, then remember your retail areas, you'd use your additional lighting power allowances in order to be able to calculate those. And so those can all show up on your interior lighting compliance check. You'd measure that against your square footages, make sure that your fixture counts are accurate, all of that good stuff. So, not to speed along too quickly, but I want to make sure we only have a few minutes left, and I want to touch on mechanical systems for some of the things that we're going to talk about here. So, getting to it. In the 24 code, we get definitions for humidification. Right. Let me go back real quickly here. Some of the things that we're going to talk about real quickly are going to be the need for high humidity, therefore humidifiers and dehumidifiers. We're also going to have CO2 enrichment systems. That's super common with this. There's other things you can run into, like ozone, number of other things. They also, this can go, like I say, down a rabbit hole when it comes to the mechanical equipment associated with these. And if it's something that you want to explore, we certainly can, but I'm just giving you the high levels of what changed between the 21 and the 24 today. So you get a definition of dehumidifier, and the first thing I want to highlight is that it's self-contained. That's going to be different from when we look at a certain code section specifically associated with dehumidification in horticulture facilities, where it does talk about mixed or hybrid systems with your HVAC system. So I want to be very clear that dehumidifiers are these self-contained systems out there. And for those that maybe have not run into these, especially in Colorado, where we're in a dry and arid climate, it's not often that we see a lot of dehumidification happening in buildings unless they're really specific uses. So we'll go over that in just a second. The other thing I wanted to highlight is we get a definition of humidistatic controls, which we're going to be using humidity as a set point, similarly to the way that we would with thermostatic controls and using temperature. So there are really two basic kinds of dehumidifiers, which are refrigerant humidifiers, which are going to use refrigeration to condense and pull moisture out of the air that way, right? Or desiccant humidifiers, and that's going to use a medium like silica gel to absorb moisture out of the air. And so when we talk about dehumidification, there's some basics here. Now, this is applied generally in the code. And like I said, there is a separate section that gets straight to the horticulture applications as well. So when we talk about dehumidification, we have these rules here about cannot reduce the dew point below 55 degrees or the relative humidity of 60% in the coldest zone served by the system. There are some exceptions that do show up for this based on specific approvals. And you notice both of them have specific approval, deadband less than 10% humidity. In this particular exception, if you pull it up, it will talk about things like hospitals, museums, very specialty sort of occupancies. And then precision areas as well. Now, like I said, we have a separate code section that specifically addresses plants and horticulture there. So it's probably best to stick with that. But there are other areas associated with maybe the plant cultivation, things like that, where dehumidification in this particular process might be more applicable, right? Places where we're not growing the plants anymore, they're stored, they're being dried, they're being turned into other materials. So one of those things that we may want to keep in mind. We also have humidification here, and it basically works the same way. We get that same sort of specific approval exception, but otherwise we're not able to use fossil fuels or electricity to produce a relative humidity above 30% in the warmest zone served by the system. Now, obviously, that doesn't fit too well when we get to some of those other things when it comes to plants because they'll probably be above that 50% or that 30% in relative humidity, more like 50, 60, 70. So one of the things that does show up here is control interlock. And basically to keep this really clear, really simple, is if the dehumidification is happening, it shouldn't be running humidification and vice versa, right? We shouldn't be running both systems at the same time. There is an exception there where we have precision related items with a no more than a 5% change in relative humidity where we would allow both systems to run at the same time. But again, that comes with specific approval. So when we get to plant growth and maintenance here, we get a few different options. And the point of this code section is really to emphasize the list of the range of strategies that you can employ. So you can do this right here, the dehumidifiers tested in accordance with these procedures, DOE 10, CFR 430. And basically that's saying you can put a federal minimum humidifier, minimum efficiency humidifier in the system. Again, we can talk about an integrated HVAC system, and we get some enthalpy out of this. We get heat recovery, designed to fulfill at least 75% of the annual energy for dehumidification reheat. The chiller system, being able to do the same thing, or we get to use a desiccant humidification system. So that's identified there separately for you. So it's really giving you the list of strategies that people can employ to try and make this successful. Now, CO2 enrichment systems, there is a number of different ways that these are produced, some of which are produced through CO2 being burned through propane or natural gas. Some of you might be looking at that going, I thought CO was produced, carbon monoxide was produced by that. So carbon monoxide is a byproduct of incomplete total combustion. CO2 is basically perfect combustion, right? It's also what you breathe out or exhale. And I've got a couple of slides at the very end of this to kind of mention that and go over it, but we might kind of cruise by those given the time. So these systems can help produce that, but remember, this is through propane or natural gas. If you're an electrification oriented community, that might be really hard to bring in any of that equipment, right? Or to use that equipment. So you might be saying, hey, you're going to have to use something else like this. So there are pure CO2 distribution systems. There are also boiler condensing systems. I think these are really cool. I'm going to mention this in a second. And then slow release systems, which is basically a bag that's going to slowly discharge CO2. People might be wondering, well, what about CO2 poisoning concerns? And so what I want to point out for you is that normal levels, 3 to 600 parts per million, that's what you're living in every day, no matter what you do. Grow levels are typically 1,000 to 3,000 is what they're shooting for an ideal environment. OSHA gets real concerned at 30,000 parts per million, right? That's significantly more than these areas right here. This becomes lethal at 100,000 parts per million, where your blood actually becomes acidic at that point, and yeah, your system can no longer carry oxygen. So very scary, but at the same time, when they talk about this, they are talking about levels significantly lower than those thresholds, right? And so I really want to highlight that for you here. Carbon dioxide versus carbon monoxide. So, oh, yeah, sorry about that. So this is carbon dioxide, right? Oh, I'm sorry. I think I actually made a copy of the same slide twice there. I'll see if that's fixed. But basically, what we're talking about here, carbon monoxide is a byproduct of combustion. It's inherently toxic all by itself. Carbon monoxide, or excuse me, carbon dioxide is what you breathe out. It's CO2. It's what the plants want to eat. It's what they need in terms of their enrichment. And so that's what those systems are trying to provide for you here. And it's significantly less hazardous than carbon monoxide, just as a reminder for everybody there. And I do apologize. I will make sure that this is fixed for anyone that wants to download a handout later on or that kind of thing. So I did mention at the very last minute there that whole thing about a condensing boiler system, and this is kind of cool. So this is a fuel fired boiler system that the exhaust actually takes out CO2, and then it's put through a condenser that then is run through a damper system to a blower. So basically, there are systems out there that can capture their own CO2 for the heating of the building itself, and then turn that into food for plants. So this is, one of those interesting strategies out there for trying to hit that sort of net zero goal using those maybe existing, gas-fired appliances, replacing them with something that can lead to some additional efficiencies. But again, this is an important component if you're talking about whether or not you're headed towards that electrification sort of desired outcome. Because if it is, then this becomes obviously, this is not something that probably be supported in the future. Could the condensing boiler system potentially be geothermal with electric? Well, that's a great question, Aaron. That is a great question. Without the combustion, I don't know whether or not a system like that would produce CO2 because I think that is a great question. I need to think about that. I will do some research and get back to you because I can't think of a system that would not be able to do that without combustion, but that doesn't mean like that's not my expertise necessarily. I'm much more energy code oriented as kind of a generalist. I will do some digging and I'll reach out to a friend at AHRI to see if they have any suggestions. So I'll try and get back to you on that if that's all right. Cool. So to wrap things up, guys, I know I'm going 2 minutes over here. I'll try and be brief. We've got some excellent offerings for you in June here. I hope you got the newsletter for this past week. This one is basically saying, hey, we've got 3 4-hour trainings planned for you starting June 10th to start going over the 2024 Energy Code as an absolute deep dive. So we'd be going over the thermal envelope, basically MEP requirements here and then efficiency packages June 10th, 17th, and 24th. And these are 3 4-hour trainings. So that could be a major component of the CEUs that you need on a topic that I think a lot of people are hungry for. So if you want to register, please go ahead and take advantage of that. We will also be doing our manual JD and S class backed by popular demand. So please join us July 1st for that one. That informs you guys how do we read those documents and how does it inform our field inspections. And we'll be covering the 21 and the 24 for any changes or updates to that as it relates to your mechanical systems on residential. So that's our first month here. And then July, what would that be? July 8th, we'll be picking up with a commercial 3-part series as well that we'll be advertising shortly as soon as we finalize some details there. So we've got basically 4-hour trainings every week starting June 10th for you to make sure everybody's ready as this transition occurs towards the new energy code and what they're doing with the state. So that's the plan. As always, take advantage of the helpline. I know some folks on here do, and it's very much appreciated. You guys make my day when you ask me good questions that require me to get in and do some real research and chat with people. And you'll have a survey at the end of this guy. Please take it. Please fill it in. Let us know how we did. Let us know if this was helpful for you and anything else that you guys would like. But yeah, otherwise, you have my email address. I'll hang out for a couple of minutes for any other questions, anything else wants to run by me. Otherwise, have a great rest of your day and really appreciate you hanging out with me for lunch.